a series on differential equations for undergraduate students. Today's lecture is on second order partial differential equations. Till now we had learned about the first order partial differential equations. We had learned the method to solve the first order partial differential equations using the method of characteristics that we had learned in the linear and semi-linear equations. So, before starting the second order partial differential equation, let us just do one example which is showing us how to solve the first order partial differential equation, which is quasi-linear. So, method of characteristics in quasi-linear equation. Let us see the example. Consider this initial boundary value problem. U square del u over del x plus del u over del t is equal to 0 for x positive and t positive, with initial condition u x 0 is equal to root x and for x greater than 0, and the boundary condition u 0 t is 0 for t greater than 0. We are just going to use this method of characteristics. That says is that we will change the function to the partial differential equation to the ordinary differential equations using the characteristic curve. For that curve we assume that it should be in the x t plane. So, we assume the parametric form as x as x r and t as t r. In that case, if we use the chain rule, we do get that du by dr we can write as del u over del x times dx over dr plus del u over del t times dt over dr. So, we get and compare this with the given equation u square del u over del x plus del u over del t is equal to 0, because there is quasi-linear. So, the coefficient of the derivatives may be the involving the function of u and the lower derivative. So, here the lower derivative would not be anything. So, it is just u square. Now, if I compare with this given equation, so we do get is that is the dx by dr would be u square and dt by dr would be 1. So, dx by dr is u square, dt by dr is 1 and du by dr is 0. So, what we are getting is that this given partial differential equation changes to the ordinary differential equation in what manner, as du upon dr is equal to 0. Now, let us see is that what it is saying is dt by dr, this is saying is that u is constant along the characteristic. Moreover, dx by dt is u square, because dt by dr was 1, that says is t is same as r. So, I can write dx by dr as u square as dx by dt is equal to u square. Now, u is constant because we have changed the ordinary differential equation, we have got du by dr is equal to 0, that says u is constant, that means u square would be constant here. So, treating it as a constant along this characteristic, if I try to solve this differential equation, we get that x is equal to u square t plus x naught, that is constant with respect to x. Now, at t is equal to 0, now we are using this initial condition, that is at t is equal to 0, x must be equal to x naught from here. From here, if I try to find out what is x naught would be nothing but x minus u square t. So, the condition which is been given that u at x naught is f of x naught, that is I would get f as f of x minus u square t. Now, at t is equal to 0, u x naught 0, that is u of x minus u square t at 0. So, what we would get the solution u x t, now substitute this one, we get the solution as f x t. What is f x t? F x t, for the initial condition was given to us was square root x. So, we are getting that is f of x is given as square root x. So, we have got u x t as square root of x minus u square t. So, we have got the solution as u x t as square root of x minus u square t, and this solution is valid on the cases when this x minus u square t is positive. Now, this is implicit solution because we are involving u here as well as in the solution. So, to find out explicit solution, that is u in the terms of x and t only, let us simplify it. So, what we do is square on both the sides, we get u square is equal to x minus u square t, which says is that u square times 1 plus t is equal to x, or u square is x upon 1 plus t. So, what we would get u as square root of x upon 1 plus t, and this square root we do want is that is real solution. So, x and t both has to be positive. So, for all x positive and for all t positive, the given partial differential equation has got the solution as square root of x upon 1 plus t. This is explicit solution because u we are getting in the terms of x and t. Let us check that is whether it is satisfying our given differential equation. We can check that this is a solution. The given differential equation is u is square del u over del x plus del u over del t is equal to 0, and the solution we had obtained with the initial condition that u x comma 0 is square root x and u 0 comma t as 0. So, we have got the solution that u x t is square root of x upon 1 plus t. So, first find out del u over del t, that is half times x to the power half into 1 plus t to the power minus half, and if I differentiate that we can write it as 1 upon 2 times square root of x into 1 plus t. Now, if I differentiate u x t, that is square root of x upon 1 plus t as with respect to x, we do get it as minus 1 by 2 square root x 1 plus x to the power minus 3 by 2. So, we are getting is minus 1 by 2 x upon 1 plus t cube. Now, put it over here, u we have got square root of x upon 1 plus t. So, u square del u over del x is x upon 1 plus t into del u over del x is 1 upon, this is del u over del x, this is 1 upon 2 times square root of x into 1 plus t, which is same as 1 upon 2 times square root of x plus 1 plus t whole cube, which is same as actually minus of del u over del t. That means, this would satisfy this equation. Moreover, if I put t is equal to 0 in our solution, I would get only square root x, and if I put x is equal to 0, we would get the whole solution would be 0 for all t. So, this is what we are getting it. So, this solution which we had obtained, that is satisfying this one. So, this is the method of characteristic in quasi linear equation of the first order partial differential equation. Now, let us come to the second order partial differential equations. First, we will treat again the equations in two variables only, that is one space variable and one the time variable. We will just take it this kind of equation, that del 2 u over del t t is equal to c square times del 2 u over del x 2, where I do have only two independent variables x and t. Normally, I will take the two independent variables as x and t. Of course, we can take x and y as well also, that does not matter, just only thing is that two independent variables and the dependent variable or the unknown function is depending only on the two variables. This is also second order partial differential equation with the two variables del u over del t is equal to c square del 2 u over del x 2. What we will try to see, as in the case of first order partial differential equations, what we tried how to find out the solution, we said that the solution is a surface because it is in the two variables. So, we try to find out in the plane containing this with the variables x and t a curve which says is that my function is constant along that curve, that is what we call the characteristic curve. And if this character we are getting is that this is happening, then we said is that Cauchy problem said is that is we would always get a solution, and with boundary value problem or initial value problem we can get the unique solution. So, here just like as the first order case, here also we will try to find out the Cauchy problem, that is we will try to find out the characteristics, that is can we get some curve in x t plane such that u is constant along that, and that is guaranteeing us a solution to the with the side conditions. So, for that again we would look for the characteristics, because it is a second order equations. So, rather than getting one characteristic, we may get more than one characteristics, and according to this number of characteristics actually we are characterizing, or you could say is we are making the types of the differential second order partial differential equations. So, first we would be considering only linear partial differential equations. Linear partial differential equations means that is my derivatives, they are occurring linearly. Moreover, because we are treating second order partial differential equation, rather than taking strictly linear partial differential equations, we will treat that is the second order derivatives, they are occurring linearly, that is their coefficients are not depending on u. It may depend on the independent variables x and t, that is you could say as linear and semi-linear kind of things we are talking about. In this case, this characteristics, that is the number of characteristics when we try to find out the curves in x and t such that u is constant along them, then we do find it out that these number of characteristics are going to actually decide about the kind or the type of the equations, and this is what is we are calling the classification and types. Basically we do get three types of our the classification says is either the equation is hyperbolic, or it is parabolic, or it is elliptic. These three types are very important in the theory of partial differential equations, because they give how to solve these particular problems, because unlike in the ordinary differential equations, we are not having here general solution for all the cases or some kind of things. Rather we would be getting is that is first deciding the type of the equation, and then we will try to change it to the certain forms, and then we will try to find out the solutions. Those things we will learn later on. Let us first learn this classification by the method of characteristics. So, classification by characteristics. Let us take this general linear differential equation, which is linear in the second order derivatives, that is I am taking del 2 u over del x2 with coefficient a, which may depend on x and t, but not on u. So, let us say in general I am writing a linear second order partial differential equation as a x t del 2 u over del x2 plus b x t del 2 u over del x del t plus c x t del 2 u over del t 2 is equal to a function. So, here this d we are denoting is as a function d of x t u del u over del x del u over del t. Why I am not writing here anything, why I am calling it a function? Here what we are saying is that I am taking this second order differential equation, which is linear in the second order derivative. With the first order derivative, it may contain the coefficients of containing u also, or u may contain the coefficients as any other thing. So, we are just treating this part as the general part. We are talking about the linearity only in the second order derivatives. This kind of equation we are calling principally linear, and this left hand side of this equation, that is a x t del 2 u over del x2 plus b x t times del 2 u over del x del t plus c x t times del 2 u over del t 2, that is all the second order derivatives and their coefficients. This part is being called the principal part of this principally linear differential equation. Now, with this differential equation, with this principal part, only this principal part is going to play a role to find out the characteristic. And how we are finding it out? The characteristics are obtained from that principal part. You see is that is you have got the coefficients a, b and c, where a was the coefficient of the second derivative partial derivative with respect to the one variable x, and b is the coefficient of the second partial derivative with a joint, that is derivative with respect to x and t both, and the c was the coefficient with the derivative with respect to the second variable. So, we get the characteristics we are obtaining by this linear this ordinary differential equation. dt by dx is equal to b plus minus square root of b square minus 4ac upon 2a. Now, here b and a, b, c all are the function of x and t. Now, because this square root of b square minus 4ac, this will give me three cases. The first case, when b square minus 4ac is positive, what I would get? I would get here that it is positive. So, some square root, some real number. So, b plus minus, that is I would get two characteristics, that is I would get the two equations which will give me the characteristics, that is one is with b plus square root of b square minus 4ac upon 2a, another is b minus square root of b square minus 4ac upon 2a, both would be real. So, we will get two characteristics, and in this case this given equation axt del 2 u over del x2 plus bxt del 2 u over del x del t plus cxt times del 2 u over del t2 is equal to d times x d of xt u del u over del x del u over del t. This is called hyperbolic. So, when we are getting is in this equation, these coefficients we are getting such that b square minus 4 times ac, this is coming as the positive, we call this equation to be hyperbolic. Second case would be, that is this b square minus 4 ac is 0. In that case what I would get, this equation dt by dx is equal to b plus minus square root b square minus 4 ac upon 2a, because b square minus 4 ac is now 0. So, I would get only single equation dt by dx as b by 2a, that says is only one characteristic, and in this case my equation axt del 2 u over del x2 plus bxt del 2 u over del x del t plus cxt times del 2 u over del t2 is equal to d of xt u del u x over del u t. This is called parabolic. Then the third case, when this b square minus 4 ac is negative, what it says is, in this characteristic what I would be getting, I would not be getting a real root, what I would be getting is that imaginary roots, and it are the complex roots, that is we are not getting any real characteristics. So, in this case this equation is called elliptic. So, we are finding out the, for this equation axt del 2 u over del x2 plus bxt del 2 u over del x del t plus cxt times del 2 u over del t2 is equal to a function of xt u del u over del x and del u over del t. This equation we would call hyperbolic, parabolic or elliptic according to my b square minus 4 ac is positive, equal to 0 or negative. And in that cases the characteristics we are finding out using this equation dt by dx is equal to b plus minus square root of b square minus 4 ac upon 2a, and depending upon these cases we are getting that is either 1 or 2 or none real characteristics. All these things when I am talking about at a particular point x and t, that is at a particular point t is equal to t naught and x is equal to x naught, we are talking about these things, these types of the equations. So, if these a, b and c are constant, then of course, the equations would be of these types hyperbolic, parabolic or elliptic for all x and t. If they are depending on x and t, then for each x these types would change. Let us just try to do some examples to understand this concept. Let us take the first example, del 2 u over del x2 minus del 2 u over del tt is equal to 0. This is one equation, second order partial differential equation. Its coefficient of the second order derivatives are constant. So, it is principally linear. In this one, if I treat the coefficient of del 2 u over del x2, that is 1. So, a is 1, del 2 u over del t2, this coefficient of second with the second partial derivative with respect to second variable is minus 1, and there is no term containing the derivative with respect to both x and t variables. So, b is 0. What we are getting, b square minus 4 ac, from here we would be getting is 0 minus 1 into minus 1, that is plus 4, which is positive. So, this equation is hyperbolic, and the characteristics would be given by b plus minus square root of b square minus 4 ac upon 2a. So, we get here since b is 0 and b square minus 4 ac is 4, we would be getting plus minus 2 by 2, that is plus minus 1. So, we are getting the two equations dt by dx is equal to 1 and dt by dx is equal to minus 1, and that would give me the two characteristics, those characteristics curves we would be calling t is equal to x plus c 1 and t is equal to minus x plus c 2. So, here I have written both the curves in single equation, that plus minus x plus c. So, here the c is the constant with respect to x. So, we can treat it in one equation as c1, another equation as c2. So, the constant is may be different, may be same, depends upon that is what the side conditions we do get. Let us do one more example. Del 2 u over del x 2 minus del u over del t is equal to 0. Now, you see the coefficient, that term containing the second order derivative is only single one, then there is one term which is containing the first order derivative. So, it is a constant, again it is of the form of the principally linear equation. In this one, a is 1, b is 0 and c is 0. So, what I would get, b square minus 4ac, b is 0, c is 0. So, b square minus 4ac would be 0. That says is this equation is parabolic. Now, what will be the characteristic? Characteristic we are getting is by b upon 2a, because b square minus 4ac is 0. So, b is 0 actually here. So, what I would get is that dt by dx is equal to 0. So, what will be the characteristic curve? Characteristic curve would be that t is a constant. So, this is only single characteristic we are getting. This is a parabolic equation. Let us do one more example. Del 2 u over del x 2 plus del 2 u over del y 2 is equal to 0. Here you see is I have taken the two independent variables as x and y rather than x and t. So, we will treat y as similar as the t. Now, again this is second order differential equation. The coefficient of second order derivatives, they are constants and we are not having any other terms. So, again we can term it as a principally linear, actually this is linear one. Here what is a? The coefficient of this one is 1, b is 0 because I do not have any second order derivative with respect to both the variables, and we do have c is equal to 1. So, what will be b square minus 4ac? b is 0. So, minus 4ac would be minus 4, which is negative. That says is I will not get any, this is simply negative, says is it is elliptic and I will not get any real characteristic. Now, from these characteristics and these three typical kind of equations, in all these examples we have got that my coefficients were constants. Now, let us do one example where the coefficients are not constant. So, let us take this Trichomy equation, which is del 2 u over del t 2 minus t times del 2 u over del x 2 is equal to 0. Now, again it is a second order differential equation where the coefficients of second order derivatives of with respect to t, this is 1, and with respect to x it is minus t. So, it is not taking the term u, it is depending on x and t. So, again it can be treated as principally linear equation. Now, what is being given? A is the coefficient of with respect to derivative with respect to x, the coefficient is minus t, b is 0 and c is 1. This says is b square minus 4ac, b is 0, minus 4ac would be 4t. Now, this is depending upon the value of the t. So, now if t is positive, negative or 0, accordingly we will get the type of equation. So, let us take, if t is less than 0, then this equation is elliptic and we will get no real characteristic. If t is equal to 0, then this equation would be parabolic and we will get single characteristic, and if t is positive, then we would get, and in the case of this t is equal to 0, the one characteristic we would get dt by dx is equal to 0, says is t is equal to c, and for the case t greater than 0, the equation would be hyperbolic and the characteristic would be given as two characteristics. Here what is my b is 0 and b square minus 4ac is 4t. So, I would be getting it plus minus 2 times square root 2 t divided by 2a, a is minus t. So, 2 minus 2 times t, that is what we are getting is plus minus 1 upon square root t. So, what will be those characteristics? By solving these equations we would get it simply 3x plus minus 2t to the power 3 by 2 is equal to c. Actually, we are getting two equations. One is 3x plus 2t to the power 3 by 2 is equal to c1. Another equation 3x minus 2t to the power 3 by 2 is equal to c2. So, depending upon the value of t, here we are getting these three types in the same equation, that is same equation can be elliptic, parabolic or hyperbolic. So, this is one example. Now, let us see how these characteristics or this finding out the characteristics help us in finding out solution of partial differential equation. But before going to the solution of this second order partial differential equation, let us see one more step in between, which says is we can give a normal form of a general second order principally linear differential equation, that is called canonical forms. They are also termed as normal forms. What is this canonical form? It is saying is that is because we were having the equation in two independent variables x and t. If I change them to another variable, say v and z. So, let us see if I do have this general principally linear second order differential equation a x t del 2 u over del x 2 plus b x t del 2 u over del x del t plus c x t times del 2 u over del t 2 is equal to a function of x t u del u over del x and del u over del t. If I introduce some new variables instead of this variables independent variables x and t, if I introduce some other new variables v and z, again there has to be a function of x and t. So, if I introduce two another independent variables v and z of the function of x and t, how this transformation? This transformation should be such a manner so that I get this principal part in a simpler form, plus this right hand side part is also something very simple form. What do we mean by simpler form? You see, we have done three examples, first three examples where we have got the equations were hyperbolic, parabolic or elliptic. The principal parts of those equations are actually coming up as a normal form. Let us see one by one these kind of cases, that is how to find out this transformation and why do we call them as the normal form, what they are helping us in finding out the solution. So, let us try to see here, that is if this changes principal part to the simpler form, we call it the canonical form. How we are using this transformation? As I said is, let us see, we are going to use the characteristics. So, let us take the first case as canonical form of parabolic equation. Parabolic equation means b square minus 4ac is 0. That says is I would get only single characteristic given by the equation dt by dx is equal to b upon 2a. If I integrate this one, I would get integral as phi x t is equal to c. So, we are just writing it, that is maybe whatever it may be depending upon whether b and a are the function of x or t or something like that, we do get its integral as phi x t is equal to c. This is single equation. So, what we will introduce the new variables of transformation, we would introduce v as phi of x, that is whatever this integral we have got from this characteristic equation, that is integral this gives me the characteristic curve. So, we are taking that characteristic curve, the left part of that characteristic curve as that phi of x t, that is the one variable. Another variable z, because this is giving the parabolic equation and this is giving me only single characteristic. So, the other variable we are taking as any variable, any function of x and t. Only thing we keep in mind that this function has to be twice differentiable, because all these variables should be in such a manner that they should possess the second order derivative, so that I could transform them into the equation, and moreover I should not get them to be this z has to be independent of v, linearly independent of v. How we do get this z linearly independent of v, that we will understand in the example actually. this transformation if I introduce in this given equation, then this would change my this equation to as del 2 u over del v 2 is equal to d bar. Now, this is another function v z u del u over del v del u over del z. That is, the principal part is being transformed, that is here in the original equation in the principal part we might have all the three kind of derivatives, while when I introduce this parabolic equation, I introduce this transformation in the principal part, I may get only the second derivative with respect to one variable only. And of course, the right hand side can contain the function of v, z, u and the derivatives with respect to v and z first order one. So, this you see is that principal part has been transformed. Now, how do we choose this z? As I said, is z has to be chosen independent of this. A normal practice is, that is, we choose z as the first variable or the other variable. So, we do use z is equal to x or z is equal to t. Whether we should choose x or t, that depends upon that the choice has to be such that this right hand side is very much simplified. In certain cases, some special cases, we may get it only a derivative with respect to the second variable, that is, my equation would reduce to del 2 u over del v 2 is equal to del u over del z directly. Now, you see if this we compare with our examples, we have got in the second example where we had del 2 u over del x 2 minus del u over del t is equal to 0, that was a parabolic equation. So, in that case this could be called as the normal form of the parabolic equation. So, that is why we are calling those examples as the typical kind or the normal form of the or canonical form of the equation. But it is not necessary that we may always get this kind of thing, but we try to use the transformation in such a manner, because here we do have a choice that we have only one equation, that is one variable we are transforming, the other is with our choice. So, that choice we treat it as that it should be linearly independent of v and it should simplify my right hand side to maximum extent. Let us take the case of canonical form of hyperbolic equation. Hyperbolic equation means b square minus 4 ac has to be positive. That says my characteristics would be given by dt by dx is equal to b plus minus square root of b square minus 4 ac upon 2a. This will, because b square minus 4 ac is positive. So, we will get the two equations. So, let us say that two equations. So, two characteristics I would get, let us say phi of x comma t as c1 and psi of x comma t as c2, because we would be getting that two differential equations, their solutions we are writing as actually the solution would be t is equal to x and this implicit one we are writing phi of x t and psi of x t is equal to c1 and c2. So, we introduce the transformation v as phi of x t and z as psi of x t, then this given equation will transform. So, now what we would do is we find out the del 2 u over del x 2 in the form of new variables v and z. Explicitly how to do all these things we will learn through the examples. So, that this equation is reducing to this kind of equation, that is the derivative of u with respect to v and z, the second derivative with respect to first and second variable both, and there should be some function of v z u, first derivative with respect to v and first derivative with respect to z. Again, this is called the canonical form of hyperbolic equation. Now, this is not matching with our example. What we do have is that if we use another transformation after this, what is that transformation? Mu as v plus z and neta as v minus z with half of this one, or you could say as we are using is v as mu plus neta and z as mu minus neta. So, this mu and neta, the new variables we are introducing. If I introduce these new variables, then that canonical form would get changed to del 2 u over del neta 2 minus del 2 u over del mu 2 is equal to some function of mu neta u and the first derivative with respect to mu and the first derivative with respect to eta. This is also known as the canonical form of the hyperbolic equation. Now, if I compare this with respect with our first example, there we have got del 2 u over del x 2 minus del 2 u over del t 2 is equal to 0. So, this left hand side, this is matching with the left hand side of our first example. So, that left hand side is actually the normal form of the hyperbolic equation. Again, when we are introducing this thing in the special cases, the right hand side exactly we could get it as 0, that is matching with that equation, and we do know that this equation is nothing but the one dimensional wave equation, that is a special case. Now, come to the canonical form of elliptic equation. That means b square minus 4 ac should be negative. In this case, what we will get? Complex conjugate characteristics, that is characteristics would be given as b plus minus square root of b square minus 4 ac upon 2a. Since this is b square minus 4 ac is negative, so whatever this is square root, we could write it out as b plus minus iota times some real number, that iota means square root of minus 1 I. If I try to solve this equation in that form, let us say the solution would be the complex conjugate ones, that is phi x t plus I of psi x t is equal to c. Then the new transformation which we would introduce, they would be of the form, that is v is equal to phi x t and z is equal to psi x t. So, what we are getting is actually we are getting the complex conjugate equations, and from there the solution also we will get the complex conjugate. So, we just try to see is that is we are treating this as one equation, and from there we are getting this complex conjugate solution. So, both this phi and psi, they are real parts. So, we are introducing the transform using these real parts. If I introduce these transforms, we get our given equation to be transformed to the form of del 2 u over del v 2 plus del 2 u over del z 2 is equal to a function of v z u, again the first derivative with respect to v and the first derivative with respect to z. In certain special form cases, this right hand side may reduce to 0, and then we do get that our example 3, even if here the left hand side is same as that the left hand side of the our example 3. So, the first, second and third examples which we have done, where we have tried to find it out the type of the equations, they are basically the canonical forms of those hyperbolic, parabolic and elliptic equations. This is if also we do know that this is nothing but the two dimensional Laplace equation. Let us see is that is how we are really transforming it. So, let us do some examples. Change the given partial differential equation to the canonical form. The equation is del 2 u over del x 2 plus 4 times del 2 u over del x del t plus 4 times del 2 u over del t t is equal to 0. Now, you see that is our equation is not very difficult in that sense. Our coefficients are with are constants. So, let us first check it, that is what is the kind of or what is the type of this equation. So, we do have is a is equal to 1, b is equal to 4 and c is equal to 4. So, b square minus 4 a c would be 16 minus 16, that is 0. So, this is a parabolic equation. Parabolic equation means that is my characteristic would be given by b upon 2a, b is 4, a is 1. So, b upon 2a, that is 4 upon 2, that is 2. So, what we would be getting is the characteristic curve would be t is equal to 2x plus c. So, this is the one characteristic only we are getting now. Change it to the canonical form. So, transformation we would introduce v as 2x minus t. What we have got the curve is that x is equal to t is equal to 2x minus c, that we are writing as 2x minus t, and the other form z is equal to x. You can just check that is this is now going to transform it. So, now what we would be using? We would be using the chain rule. Z I have chosen as x. We do know that is here z, the choice of z is just ours, that is we have chosen z such that it should be linearly independent. Linearly independent means is if I find out all the derivative with respect to x and t for both the variables, del v over del x is 2, del v over del t is minus 1, del z over del x is 1 and del z over del t is equal to 0. So, if I take the Jacobian 2 minus 1 1 0, I would get it 1. So, this is not 0. So, that says it is linearly independent. Now, using the chain rule, we get del u over del x, we can write del u over del v into del v over del x plus del u over del z into del z over del x. Now, substitute this del v over del x and all those and del z over del x over here. What we get is 2 times del u over del v plus del u over del z. Now, find out the second derivative, that is derivative of del u over del x. So, we are again differentiating with respect to v and writing the derivative with respect to x. So, del of del v of del u over del x, that is 2 times del u over del v plus del u over del z times del v over del x plus the derivative with respect to, sorry, it should not be u, it is del upon del z of u times del u over del v plus del u over del z and multiplied with del z over del x. Again del v over del x is 2 and del z over del x is 1. What we do get is, that is when I operate this del upon del v over here, I would get 2 times del 2 u over del v 2 plus del 2 u over del v del z. This place we would be getting is, this u is not there. So, del upon del z, when I am operating over here, I would get 2 times del 2 u del z del v. Now, what we are assuming is that the continuity is being contained. So, whether we write del 2 u over del v or del z or del 2 u del z del v, both we are treating as same. Thus, we would get is 4 times del 2 u over del v 2 plus 4 times del 2 u over del v del z plus del 2 u over del z 2. Similarly, we will find out del 2 u over del u over del t, again using the same kind of chain rule, del u over del v over del t plus del u over del z and del z over del t. Now, del v over del t we have got minus 1, del z over del t is 0. So, we do get it as minus del u over del v. Now, the second derivative with respect to this, again we go with the same rule. So, del upon del v minus del u over del v over del t minus del over del z of minus del u over del v del z over del t. Again put it, that is del z over del t is 0. So, what I would be getting is this minus 1 minus minus will get plus 1 and I would be getting is only simply del 2 u over del v 2. From here we will try to find out del 2 u over del z del t, del u del t. So, del x del t we are getting. So, that is we are differentiating with respect to x. So, del upon del v of minus del u over del v into del v over del x plus del upon del z of minus del u over del v of del z over del x, which is again we are getting del v over del x was 2 and del z over del x was 1. So, I would be getting minus del 2 u over del v 2 minus del 2 u over del v del z. Now, substitute these in the given equation. So, the canonical form of this equation, this is the given equation. Now, I will substitute del 2 u over del x 2, del 2 u over del x del t and del 2 u over del t 2, whatever we have obtained that form of our derivatives with respect to v and z. So, the new variables, the first one if you do remember, we have got 4 of del 2 u over del v 2 plus 4 times del 2 u over del v del z plus del 2 u over del z 2, then plus 4 times del 2 u over del x del t. Del 2 u over del x del t is this one. This has to be multiplied with 4 times. So, I would get minus 8 times del 2 u over del v 2 minus 4 times del 2 u over del v and del z and plus 4 times del 2 u over del v 2 is equal to 0. Now, we see is this del 2 u over del v 2 with 4 coefficient, it is with minus 8 and this is with plus 4. I will get this, cancel it out. Moreover, this del 2 u over del v del z, that is with the 4 coefficient and here is the coefficient is minus 4, again this is being cancelled it out. What is being left is del 2 u over del z 2 is equal to 0. This is what is, we are getting the parabolic equation. So, now we have got, we have chosen our second variable z as x and we have got the simplest form where the right hand side has turned out to be 0. This will actually help in solving the differential equations, that we will learn later on. Let us do one more example. So, now we do have this equation del 2 u over del x 2 minus 4 times del 2 u over del x del t plus 3 times del 2 u over del t 2 is equal to 0. we want to change this differential equation to its normal form. What we do is again first find out the type of the equation and then use the characteristic to change it to the normal form. The coefficient of del 2 u over del x 2 is 1, the coefficient of del 2 u over del x t del t is minus 4. So, b is minus 4, similarly c is 3. That says is b square minus 4 ac would be 16 minus 12, we are getting it 4, that is positive. So, this is hyperbolic equation. The characteristic is now dt by dx is equal to minus 4, that is b plus minus the square root of b square minus 4 c, that is 4 square root of 4 is 2. So, plus minus 2 by 2, that is what we would be getting two equations, dt by dx is equal to minus 3 and dt by dx is equal to minus 1. Thus, we would get two characteristic curves, one is t is equal to minus 3x plus c1, another is t is equal to minus x plus c2. So, the new transformation what we will introduce, v as 3x plus t and z as x plus t. This will give me del v over del x as 3, del v over del t as 1, del z over del x as 1 and del z over del t as 1. So, again using the chain rule we will transform, we will get del u over del x and del 2 u over del x like that one. So, del u over del x, by this again using the chain rule we would get del v over del x is 3 and del z over del x is 1. So, 3 times del u over del v plus del u over del z. Now, go to the second derivative, differentiate this once more with respect to x. So, again using the chain rule we are differentiating it with respect to v and then getting the v with respect to x, then with respect to z and with respect to z with respect to x. So, we would be getting is that del upon del v of 3 times del u over del v plus del u over del z times del v over del x plus del of del z of 3 upon del u over del v plus del u over del z times del z over del x. Again we will keep del v over del x as 3 and operate this upon similarly del z over del x 1 and operate del upon del z on this one. We will finally get 9 times del 2 u over del v 2 plus 6 times del 2 u over del v del z plus del 2 u over del z 2. You see here when we are getting is 3. So, 3 into 3 this we would be getting del 2 u over del v 2. We are again using that del 2 u over del v del z and del 2 u del z del v, they are equal. So, here the coefficient is 3 because of this 3 and here is also the coefficient is 3 because of this 3, would get 6 and so on. Now, let us move to the del u over del t. Again using the chain rule, del v over del t is 1 and del z over del t is also 1. So, we get it as del u over del v plus del u over del z. So, the second derivative with respect to t will differentiate again this with respect to this thing with respect to t. So, again using the chain rule, this would be del upon del v of del u over del v plus del u over del z del v over del t plus del of del z of del u over del v plus del u over del z over del t, which again when we apply this is 1 and this is 1. So, from here I would be getting del 2 u over del v 2, this term and this term is going to give us plus 2 times del 2 u over del v del z and plus del 2 u over del z 2. From here itself we will find out the del 2 u over del x del t, that is what we will do is that this del u over del t, this function will differentiate once more with respect to x. Using the chain rule again we would get here del v over del x and here del z over del x, and this is derivative with respect to v and this is the derivative with respect to z. Del upon del v upon del x we have got 3 and del z upon del x as 1. So, what we are getting is 3 times del 2 u over del v 2. From here we would get 3 times del u over del 2 u over del v del z and from here 1 times del 2 u over del z del v, we would get 4 times del 2 u over del v del z plus del 2 u over del z 2. So, now we have got all the 3, that is del 2 u over del x 2 as 9 times del 2 u over del v 2 plus 6 times del 2 u over del v del z plus del 2 u over del z 2, del 2 u over del x del t as 3 times del 2 u over del v 2 plus 4 times del 2 u del v del z plus del 2 u del z 2 and del 2 u over del t 2 as del 2 u over del v 2 plus 2 times del 2 u over del v del z plus del 2 u over del z 2. Now, substitute this in our given equation to find out the canonical form. So, the given equation is del 2 u over del x 2 minus 4 times del 2 u over del x del t plus 3 times del 2 u over del t 2 is equal to 0. So, substitute it here. What I would get instead of this del 2 u over del x 2, we would write 9 times this del 2 u over del v 2 plus 6 times del 2 u over del v del z plus del 2 u del z 2 minus 4 times. So, multiply this with, so I would get the coefficient of del 2 u minus del v 2 as minus 12, the coefficient of this second derivative with respect to both the variables as minus 16, and the derivative of this is minus 4, coefficient of this one, plus 3 times del 2 u over del t 2, that is multiply this with 3 and add it over here. So, 3 times del 2 u over del t v 2 plus 6 times del 2 u over del v 2 plus 3 times del 2 u over del z 2. This has to be equal to 0. Now, let us see in this equation. First, take the terms involving second derivative with respect to the variable v. Del 2 u over del v 2 coefficient is 9, del 2 over del v 2 coefficient is minus 12, del 2 u over del v 2 coefficient is plus 3. So, 9 plus 3 is plus 12 and minus 12, this will cancel it out. Coefficient of del 2 u over del z 2, this is 1 plus 1 here, here it is minus 4 and here it is plus 3. Again we will get 3 plus 1 is plus 4 and minus 4. So, again this term involving the terms of del 2 u over del z 2, they are been cancelled it out. Then what we have got the terms involving del 2 u over del v del z. The coefficient here is 6, the coefficient here is minus 16 and the coefficient here is plus 6. So, 6 plus 6 12 and minus 16, what we are getting is minus 4 times del 2 over del v del z. Since minus 4, so I can divide this equation by minus 4. What we would be getting is actually del 2 u over del v del z is equal to 0. So, this is what you are getting is that for hyperbolic equation, this is the canonical form which we are getting. These canonical forms are helping us in getting the solution. What you are seeing is that is the equations which we are having. Of course, in both the examples I have taken that little bit simpler one, that is where the right hand side was the 0. So, the only principal part we have changed to the canonical forms and the right hand side has become 0. But this says is that when we are using this kind of forms, it helps us in solving the differential equation. How to solve the differential equation of the second partial differential equation of second order, that we would see the next, and how these forms are actually helping us in getting the solution of the differential equations, that is also very important part. So, we would learn all these things in the next one. So, today we had learned that is second order differential equation, partial differential equations, which we have talked about the principally linear second order partial differential equations, where the principal part we have kept on mod I, and we said is that this principal part taking upon the coefficients of the second order derivatives, we have derived the three types of equations we have defined. Those things we have called, that is characteristics, we had find out using those coefficients, and with the help of those characteristics we had find it out, that is what is that new transformation, and with those transformation we have changed those principal parts to much simpler forms. The simpler form we have learned about the two kind of equations, parabolic and hyperbolic. In parabolic we got only one characteristic. So, for the transformation the other variable we had used with our simple intellect, that the other variable has to be linearly independent of the first variable and it should simplify the right hand side. We have got the simpler forms, that is involving only one variable or the derivatives with respect to the both the variables in the case of your this hyperbolic equations. Let us see that is how they are going to help us in solution of the differential equations. So, that is all for today. Thank you.